So guys, let's understand the skip-gram modeling. So this is not like a traditional lecture. We will talk about theoretical aspect, but instead of that, we'll try to understand how the skip-gram will work. Let's say that we have words, he is a king, and the king is royal, and she is the royal queen. Based on this complete words, we want to generate embeddings for each unique word within these sentences or documents. The first thing that we will get the unique words out from this sentences. These are the unique word within this complete sentence. Now based on these unique word, we have provided an index to each individual word. So he is 0, is 1, a is 2, queen is 3. So in that way we have provided some indexes for each individual words. Now based on these indexes we are generating this one hot encoded vectors. So one hot encoded vectors are, I will just give a brief that wherever this word is present at that index we'll put 1, and rest all index wherever this word is not present we will write 0. So if I have like he, then it is on index 0, so that's why we are putting 1 over here. So this is called one hot encoding. So the next concept over here is the word, context and window size. Let's take this is word. Okay, now this time this is a word, and the window size, we have a window size of 3, so I'm taking this 3 words within a single window. And with respect to this is word, the context is he and a. Now let's make it little more clear. Suppose we have a window size of 5, okay, instead of 3. So I will take this word the. Now the window size is 5, so I'll start from here and I will go till here. So I have 5 words within this window, 1, 2, 3, 4, 5. Okay. Now with respect to this the, I have the as in word, and a and king and is are the context for this word. Okay, this is a very important part to understand, because based on these context and words and window size we are going to frame out our neural network. Now let's look down how the forward pass of the neural network will look like. As we already discussed earlier, we are going to use a shallow type of neural network over here. So we have only a single hidden layer, and then we have an input layer and the output layer. Now let's take a simple example of is. Okay, this is this is our word. He and a are the context for this word, since I have taken a window size of 3. In case I have taken a higher window size, the context word would have been changed. So this is a vector we are feeding in. So we have to give attention to this vector size. Okay, so we have this 1 cross 8 vector which is getting fed to this neural network. Now here is the hidden layer of our neural network. So within this hidden layer we have 4 weights, okay, W1, W2, W3, W4, and then 4 biases, B1, B2, B3 and B4. As I'm showing you this in 2 dimension, it is not a 2-dimensional vector in actuality. So basically this W vector is a 3-dimensional vector, okay, and the third dimension is the dimension of like 8 vectors out there. For like this W1, I have W11, as you can see over here, W12, W13, W14, W15, W16. So in that way we have 8 vectors with respect to each individual weights and biases. For biases also, like we have B11, B12, B till B18. So we have 4 neurons for this vector. So let's check the dimensionality part. So we have 4 cross 8, this W vector, and this B vector is again 4 cross 8. Okay. Now we have to multiply this with the input vector. Now if you want to multiply this with the input vector, the dimension should match. So 1 cross 8 you cannot multiply directly with 4 cross 8. Hence you have to take the transpose of this vector. So 4 cross 8 transpose will be 8 cross 4. Now this matrix can easily multiply and you will get a 1 cross 4 matrix output from this, or a 4 cross 1 matrix. Okay. Now you might be confused like where this B has gone. Earlier it was like W. Now where is this B? So basically what happened here, like you multiply w with your input vector, it gave you like 1 cross 4. Then you also multiplied this bias with your input vector, so that will also give you like 1 cross 4. And you are doing an element wise sum, so every single element is getting added to the other element and you are going to get 1 cross 4. Okay, so these are like a sum of two matrices which equal dimensions. Now once you are done with this, it's kind of what actually happened. If you see over here, you were at 8 cross 1 and now your dimension has reduced to 4 cross 1 approx. Okay, or 1 cross 4 you can say. Your dimension has been reduced. Now you want to do some sort of prediction for the context word. So with the help of this you want to predict like this he and a. Now how to achieve that part? So for that you have to apply a softmax next to that. So as you can see, whatever outputs are coming out from this matrix, the hidden layer are fed to a softmax layer 4 cross 1, and this softmax layer converts your output to a higher dimensional space of 8 cross 1. So the output of this vector would be like 8 cross 1 again. And I'm not going to talk about softmax functionality over here because I have explained it on my YouTube videos as well as on other Udemy courses. And it is also kind of out of scope for this course. But this softmax is going to convert your vector to a higher dimension space of 8 cross 1. Now you have to do some sort of back propagation and calculate the loss, like how much error I am making on top of this. So how do you calculate this error? Now basically you have these context words like a and he, okay, and we have this one hot encoded vector for both of these words. If you see over here, I have two vectors of 1 cross 8 and 1 cross 8, okay, but the output of the model is only one vector, which is 1 cross 8. So how do you calculate the loss for this model? So what we are going to do over here, that we are going to create a copy of this vector and then we are going to calculate the loss, because the copy would be like 8 cross 1 and this is also a 8 cross 1 vector. For this first copy, we will calculate the loss between this output vector and this a, okay, and we will try to minimize this loss. So what we are trying to do over here, that we are trying to reduce the distance between this output vector and its context vector. If you see, I am calculating loss with respect to like is and a. So whatever output being generated with help of this is, I am calculating the loss with a, okay. And similar thing I am going to do with he, because he is also another context vector for this model. Now once we have done this, you are going to sum these context vectors loss. Once you will sum this loss, you will get the final loss for this. Now all things that you need to do is to calculate the derivative of this loss with respect to the weights, then update your weights going backward, okay. Now you have calculated this hidden layer weights and biases. Based on these hidden weights and biases, how you will calculate the embeddings out, okay. So earlier your embedding will, like if you have 8 words, your total vector space was like 8 cross 8 vector. Let's see what is going to happen once you are going to multiply this with your hidden layer weights. So your hidden layer weights are like 4 cross 8. Now if you take the transpose, it will be 8 cross 4, and once you will multiply this with 8 cross 8, you will get a 8 cross 4 matrix, okay. Now for each particular, because we have 8 cross 4 matrix, so you will have 8 rows and 4 will be the dimension. So you can see that instead of having 8 dimension over here, now it got converted to 4 dimension. So in that way your skip-gram model works. So it skips out a single word and then try to predict the context of that word. And the beauty lies between how we calculate the loss for this complete model. And what is the purpose of doing it is like to reduce the dimension or create a dense embedding for your word. Okay, because this is a sparse embedding, like you have one, then all zeros are there. But once you will convert to a smaller dimension space like a 4 cross 8 matrix, it will be like a dense vector. You will have some values for all these columns, and you can fix the number of space that you want to achieve. Like if you will increase the weights over here, like if you will put w5 w6, then you are going to get a 6 cross 8. Okay, you are going to get 6 vectors out there. So in that way, yeah, you can manage like how many vectors space you want to achieve after applying the skip-gram model. So this is all about the skip-gram modeling. Now I will meet you in the next lecture. Till then, bye bye and take care.